Hi there everyone. Today we're going to start paper 5 probability and statistics. This is October-November 2023. Let's get started. So question 1. Becky sometimes works in an office and sometimes works at home. The random variable x denotes the number of days that she works at home in any given week. It is given that p x is equals to x is equals to kx brackets x plus 1, where k is a constant and x equals to 1, 2, 3 or 4 only. Part A. Draw up the probability distribution table for x, giving the probabilities as numerical fractions. Alright, this is probably one of the most easiest questions in which you can score very easily. First of all, they're asking you to create a table. So how do you want your table? You're going to basically have two rows. You're going to have a row for x and you're going to have a second row to show probability that x, the random variable, is equals to that given x you're finding for. Alright, here they have made our work much easier. They have already said to us what values x can take. Usually you would have to find that on your own, so it becomes a bit of more work. But over here they have made it much more easier for us, as we already know what values x can take. Right, but now we need to find these probabilities. How do we go about finding them? Well, we have been given this expression over here. We can make use of that expression. So as a matter of fact, you should know that all of the probabilities of all the values of x that can take add up to 1. Using this fact, we can basically make expressions for all of these probabilities kx brackets x plus 1 and make its sum equals to 1, because probability of all of these, total sum of all of these probabilities would basically add to 1. So let's put that into perspective. First of all, let's see. Let's start with value of x equals to 1. So we want to have what? We want to have sum of probabilities is equals to 1. So we're going to start with the first x value, x equals to 1. That would be k. X becomes 1, that's multiplied directly, and inside we have 1 plus 1. Alright, now the next probability, that is of 2. So that would be k 2, 2 plus 1. Next we will have 3. So k 3, 3 plus 1. And then lastly we will have 4. So k 4, 4 plus 1. All of this sum should equal 1, because these are all the possible probabilities, so all of them should add up to 1. Alright, and once you will simplify all of this expression, you're going to get k is equals to 0.025. And from here, rest of the work is really easy. You just have to plug in the value of k again into these expressions, right? So your general expression basically become probability that x is equals to x is equals to 0.025 x plus 1. All we need to do is to just substitute values of x back again to fill out our table. Suppose I'm going to start for 1. Probability x is equals to 1 is equals to 0.025 1 plus 1, and that will give me, let's see, 0.025 1 plus 1, that will give me 1 over 20. So we'll put 1 over 20 over here, and similarly you will fill rest of them. So you would get 3 over 20, 3 over 10, and 1 by 2. They have asked us to write as numerical fractions, so we'll just leave them as fractions. Otherwise, we could also write them in decimals, but the question here asks us to write in fractions, so we will write in fractions. Next part, find expected value of x and variance of x. Really easy. If you don't know the formula to calculate var x and ex, you can always refer back to your formula sheet, as you are given in the formula sheet as well, right? In the formula sheet, you are given the formula of expected value of x. Part B, find expected value of x and variance of x. So again, a very easy part. First of all, write down what you're going to find. Expected value of x. So what exactly is expected value of x? That is basically your sum of x values into the probability. You're going to multiply all of these x value with their corresponding probabilities and then add all of these up to get your expected value of x. All right. So let's see, our first one was 1 over 20. We multiply that with the x value, which is 1. Next, we have 3 over 20. We multiply that by 2 as that was the corresponding x value. Next, we have 3 over 10. We multiply that by 3. And then we have 1 by 2, which we multiply by 4. Simplifying all of that gives us 3.25 as the expected value. Next, we will find var x. Again, this one is simple. The formula goes, it would be the sum of x squared values into the probability. But after this, we have another thing, and that is it would have the squared value of expected value subtracted from this sum. All right. So let's write that down. We would have 1 into 20 into 1, that would be squared anyways, 1. Then you have 2, which was the corresponding x value, multiplied with the probability, that is 3 over 20. Then you have 3 squared into 3 over 10, which was the probability. Then you have 4 squared, the x value, into 1 by 2, that was the probability. Now make sure you also write this after it, that you have to subtract the expected value. Many people lose a lot of marks just for not mentioning either the expected value to subtract from, or they forget to square the value. So it's very important you do that. All right. So after that, the value you'll get would be 63 over 80. So that is your variance of x. And that's part B done. Question number 2. The weights of large bags of pasta produced by a company are normally distributed with mean 1.5 kg and standard deviation 0.05 kg. Part A. Find the probability that a randomly chosen large bag of pasta weighs between 1.42 kg and 1.52 kg. Now, generally, the best way to start this question is to write down the general statement. This really does not carry any mark, but it helps to clarify where are your variables sitting. So we do know 1.5 is the mean. All right, in this form, we write that the variable w is distributed as a normal distribution with the mean 1.5 and standard deviation, but we mention over here variance, so we square it. That's just the standard format, so we write it in square, but of course you would use 0.05 standard deviation. Next, it's very important to write what statement you're going to find probability for. We want to look for probability that the weight, which I've denoted as w over here, is greater than 1.42 and lesser than 1.52, since we want the weight between these two values. All right. Now we always split these large probabilities down into smaller probabilities. So we can rewrite this as probability of w being lesser than 1.52 minus probability of w being lesser than 1.42. And if for some reason you cannot come up with these statements, you can always draw up your normal distribution curve. All right, so I'm going to sketch the normal distribution curve over here real quickly. Right, so in the center we have our mean. We have mean of 1.5, and we are looking for weights between 1.52. So 1.52 is greater than 1.5, so it would be somewhere over here, 1.52. 1.42 is lesser than the mean 1.5, so it would be somewhere over here. Don't need to worry about the exact positions, you just need a sketch, right? So now how did I come up with this statement on the right? All right. So what do we basically want? We want we want the weight to lie somewhere in here. Lesser than 1.52 but greater than 1.42. How do we achieve that? Well, we can achieve that by first of all calculating this area over here, all right, which is denoted by probability of W being lesser than 1.42, and then we can separately calculate this area, all right. So I'm just going to overline like this whole area of W being lesser than 1.52. Remember, lesser than lesser than Z value, it will always give you to the left side of the value you're looking for. So this probability over here would give you all of this combined blue area. And when you find the difference of both of these, you would get your yellow area, which is the target area we want to find the probability for. All right. So the very next thing now you have to do is that we have to standardize it. We have to standardize it so that it matches our given probability table. Since we can't directly work out with the value of W, we need to standardize it first, because we only have the normal distribution for values of Z. So how do we do that? We standardize it. The general formula for standardizing, which I'll also write over here, is Z value, or the Z score, let us say, let's be noted with lowercase z. The Z score is basically the value which you're doing minus the mean, not this is the standard deviation, minus the mean over the standard deviation. Make sure it's standard deviation and not the squared, because that would be variance. All right, it's very important that you show this step, because in most mark schemes this carries a whole mark for just showing this process. So we're going to subtract our 1.52 value from the mean, divide that by 0.05. Similarly, we're going to standardize our other probability. Find the Z score, that would be 1.52 or 1.52, 1.42 minus 1.5 over 0.05. All right. And this will simplify to 0.4. Forgot to mention Z. Probability of Z is lesser than 0.4 minus probability of C being lesser than minus 1.6. All right. Now we have gotten this into the Z probability. We can rewrite this using the phi, which basically is another just fancy way of showing that we're going to be using this table. So it's a much cleaner way of using this same notation. So we can now rewrite this as 0.4. Although this step is completely optional, you can just write it if you want to. And then we're going to be looking for the probability of minus 1.6. All right. Now we're going to go into our table of values. All right. This notation which we used, phi z, is basically showing the exact same thing which we had written before, that probability of Z value is lesser than the Z score we're looking for, making sure that the values which we're looking are on the left side. That's why we're going to make sure that the probability is first in this form, lesser than Z. All right, so we were looking for values of 0.4 first of all. So how do you read this table again? You look at the Z values, you see for the matching values first of all. So we have over here 0.4. After 0.4, we of course have no further digits, so we have our basically next digit as 0. So our value is very easily 0.6554 as our probability. 0.6554 minus, but now you'll notice over here our Z score here is negative. The table in fact gives us data or information on what to do if our value is negative. If our value is negative, they have told us that we can write it in this expanded form, 1 minus the probability of that same value but without the minus sign. This makes stuff much more easier for us. We can copy that here. All right, 1 minus 1.6. So we basically use that exact same formula right in our working. Now we're going to look for 1.6. So again, go into the table, start reading from the first column, and we see that we want the value of 1.6. The next digit is 0, so directly we get a probability of 0.9452. So we have 0.6554 minus 1 minus, it was 0.9452. 0.9452. And once you calculate this probability, you would get your answer as 0.6006, which you can round into three significant figures, 0.601 as your final probability. Next part, the weights of small bags of pasta produced by the company are normally distributed with mean 0.75 kg and standard deviation sigma kg. It is found that 68% of these small bags have weight less than 0.9 kg. Find the value of the standard deviation. Now again, it's best to write the general statement that the weights W of this new pasta bags are normally distributed with mean 0.75 and standard deviation sigma. Alright, and next you're going to write your statement of probability. What you're going to look for, that would be probability that W is lesser than 0.9. As they said, that weight have less than 0.9 kg. So weight, as we are using as W, less than, that would be lesser than 0.9. So that is your probability statement. And from where do you get the probability? Well, this percentage over here is also a probability. So that would be 0.68. Now in this question, we're going to basically apply the reverse process. Again, what do? We're first of all going to standardize. Always you're going to standardize first of all, because that's the only way you can make sure you can access the Z distribution table. Otherwise, you can't really use it. So we're going to standardize it. All right. We would have then probability of Z lesser than 0.9 minus 0.75 over the standard deviation is equals to 0.68. Now remember, we can also write this again as the phi symbol with the 0.9 minus 0.75 over the standard deviation is equals to 0.68. Now, why did I say we're going to apply the reverse process? Because this is a function. If we take it to the other side, we'll be basically looking for the inverse. Inverse phi brackets 0.68, and on the other hand side we have 0.9 minus 0.75 over phi. Now, how do we work with this thing on the right hand side? What is phi inverse basically? We're going to be applying the reverse process. All right. When we were working with this phi function, we were looking for the corresponding Z value and then we took its probability. But for the inverse function, we're going to be looking for the probability that we have specified, and for that probability, we're going to find and get back a Z value. All right. So we're going to go back into our table and we're going to try forming this probability of 0.68. First of all, check maybe the 0.68 value could be in the critical values. If it is, then you're lucky. You can directly pick up, if the probability is over here, you can take the corresponding Z values. If it's not, then you have to go to the table back in. All right. So let's look. So our value 0.68 starts with 0.6. So let's look at the probabilities that are having 0.6. All right. So we have over here 0.6, 0.4 Z value. We have 0.6554. All right. So we can probably check from here, because 67 or probability 0.6772. This looks a nice way to start, because 0.6808 is already greater than 0.68 probability. We're looking for the probability 0.68, noting it down here. So 0.6808 is already exceeded. So the very last value we can use is this one, but this is not where it ends. All right. Now we need to add into it some extra digits so that we can get as close as possible to 0.68. All right. So our base value over here is 0.6772. All right. Now let's see what we can add into it. Let us start with maybe 25. All right, that would be plus 0.00, we see on the calculator, 0.6772 plus 0.0025. Yes, 0.0025. So this would give us 0.6797. That's probably close, because if we're going to round, we're going to get 0.68. Let's try the next value, 29. So that would be 0.6772 plus 0.0029. We're going to be using this next value, and that gives us 0.6801. So this one value is much more closer to 0.68. All right, if we check the last value, 0.6797, this value is approximately 3 digits away from our value of 0.68, while this value is just one extra decimal value away from our value, which we're looking of 0.68. So this one is much closer. So we're going to use this value. So which z value do we take back? We're going to be taking 0.4, as this is lying in the 0.4 row, 0.4, and then 0.6. So so our z score is 0.4. We look at what value we took here, 0.46, and then what value we added, that was 8, 0.468. So that is our z value. So we come back with our z value, 0.468. That is our corresponding z value. And then we write 0.9, 0.75 on the other hand side as usual. Now we have just one unknown over here, so that easily makes the calculation simpler. Just rearrange and find out, and you would find the standard deviation as 0.321. Question number 3. Tim has 2 bags of marbles A and B. Bag A contains 8 white marbles, 4 red marbles, and 3 yellow marbles. Bag B contains 6 white marbles, 7 red marbles, and 2 yellow marbles. Tim also has an ordinary fair 6-sided dice. He rolls the dice. If he obtains a 1 or 2, he chooses 2 marbles at random from bag A without replacement. If he obtains a 3, 4, 5, or 6, he chooses 2 marbles at random from bag B without replacement. Probability of, we have to now find the probability that both marbles are white. All right. So usually for these questions, I prefer drawing a tree diagram, because we are doing multiple events one after the another. So if you're going to chain all of these events back to back, it's a good idea that you can draw a tree diagram, because it will give you all of the chains. And then simply getting the data from the tree diagram is much easier than thinking of all of the cases separately. All right. So we can, however, still write the statement, at least what they're asking for. They're asking that both marbles would be white, right? So we want probability that both are white. All right. So what do we want? Let's try making a tree diagram for this. All right. So what is our statement over here? First of all, Tim also has an order. If it's he rolls the dice, all right, and then based on the dice roll, we're going to choose from either bag A or either bag B. Okay, so let's start. So we're going to first of all start with a dice roll. All right. So for a dice roll, we have 6 values, so we can make 6 branches. We have 1, 2, 3, 4, 5, 6. All right. We don't need to note down the probabilities, because of course it's a fair die. Because it's a fair dice, all of them would have a probability of 1/6. All right. Next, what do we see? If he obtains a 1 or a 2, he chooses 2 marbles at random from bag A without replacement. All right. So let's see. We have 1 and 2. So we have chosen 1. Now, because number 1 is chosen, we're going to choose from bag A. From bag A, we're going to choose 2 marbles at random. What do we have in the bag A? We have 8 white, 4 red, and 3 marbles. So we have 3 choices after this. We have choice of getting a white, of getting a red, choice of getting a white, we have a choice of getting a red, and we have a choice of getting yellow marble. All right. But we don't need to make for the yellow branch. In fact, we can totally omit the yellow branch. Why? Because over here we're just focusing on looking at whether we have both marbles as white. So I think so we can focus on just the white branch. Yes, that would make the tree much more easier. It's usually a good way to slice down what trees or what branch do you need from the tree, because just drawing all of them you can already see it's going to be a huge tree. So it's best if you minimize the amount of branches you're going to make. We're going to focus on the probabilities of white. All right. So we want white. Of course, there are other branches as well. It's not that they have just disappeared. There are. We're just not drawing them because we're not concerned with them right now. So this is the first pick from the first pick from the bag A. Now we also need a second pick because they said we're going to choose 2 marbles without replacement. So after we have chosen white, all right, and we only want to focus on just choosing white because they said both marbles are white. So after choosing white, we again want to get probability of white. All right. And then if he obtains a 2, he chooses 2 again. So we will basically have the same branch on white. Again, note we are not just ignoring the other branch. We're not just drawing the other branches, but they are still there. So the probability will still affect, especially if we are not replacing them. Next, we see if he obtains a 3, 4, or 5 or 6, he chooses 2 marbles from bag B. All right. So this would be for bag B, two marbles. So the same case goes over here. So you can see the pattern which we're having. We will have a white, and then we want to go for another white, and same goes for 5 white, white, same goes for 4 white, and then we want another white, same goes for 3 white and another white. But these all branches, all of these will be from bag B, and the upper one would be from bag A. So these branches over here, these one will be concerned for only bag A, and the rest of them for bag B. Now we can easily work out the probability. In fact, this will also help us in the next question. So now we have clearly set out what do we want. So next we're going to see both white. What would that mean? That would mean probability that we are choosing from A. All right, because we have 2 choices basically. We either choose from A or from B. Of course, that would be determined by the dice roll. So probability, so in fact we can write it down. So we can write it down like this: probability that we have a 1 intersection, or basically and probability we have a 1, and we have white, and we have another white. Of course, we can also write that they're from bag A, but we have just automatically noted over here. So no need to write that same information again. All right, this is just one of them, one of the cases. Make sure that we are going to just multiply across the branches as we usually do, and for branches across, we're going to add them. So this whole is one case. We multiply this probability, and this is another case. So we add its probability after multiply. Second case would be 2 intersection, and because we wanted white and white, and so on for bag B as well. Probability, so I'm just going to shorten it down. Probability that is bag B. All right, this would represent all of these branches 3, 4, 5, 6, or you can write it as I did for bag A as well, 1 intersection W, and because it's understood that 1 and 2 will only lead us to bag A. So over here I'm writing B because it's understood then we're going to be choosing 3, 4, 5, 6. These are the ones fixed for bag B. So probability it's B, and it's both white. So white and white. Now we can get down to finding the probability. So for this one, we want 1. What's the probability of getting a 1? That's 1 by 6. All right. Next, multiply, because we're still on the same branch, probability of getting a white. So we're in bag A. Currently we have 8 whites, and total how much? 8 plus 4 plus 3. So we can sum them. 8 plus 4 plus 3. We have 15 from which we can choose. All right. Now we're going to choose another white, but you have to notice that we did not replace our white marble. So we're going to have one marble less. So now we're going to have 7 white marbles, and of course 14, because one marble has just been taken out. That's our one case done, and we can simply multiply this by 2 because these two cases are identical. The probabilities are really same. And then, because we're still choosing from the same bag, and now for the probability of B, we are going to see we have 3, 4, 5, 6. So probability of each branch is 1 by 6. All right, let's do it one by one for one branch. Let's take first of all 3 branch or any branch. So first of all, for getting that number, the probability would be 1 by 6. And let's see how many whites do we have. That would be 6 white. And then we see what's the total. 6 plus 7 plus 2, 15. 6 over 15. And then as one marble has already been taken out, we'll have 5 white marbles to choose from next time for the second marble pick. And over 14. All right. And we'll be multiplying these by 4. Why 4? Because the same case will basically be for branch 4, branch 5, branch 6. Exact same probabilities. So 4 times. Simplifying all of this gives us 0.184 as our final probability. And that's this question done. Part B. Find the probability that the 2 marbles come from bag B, given that one marble is white and one is red. Now this question may just look a bit confusing because they are adding different probabilities here and there, left and right, but it's really just a conditional probability. You can first of all, of course, write down the statement. We want that the 2 marbles are from B. All right. Given that, given we are going to use the pipe symbol, given that one of the marbles is white and the other one is red. All right. Expanding this, we're going to write it into the general form, which would be probability of B intersection or and probability of B, and the first is W and the second one is R. Not necessarily the first one, it should be that one is white and one is red. They can interchange, of course, over probability that it's a white and a red. And now we can simply find the probabilities for this, and it is very easy because we have already made a tree diagram. So we can look for the numerator first of all. We have B intersection, first is W, one is W and one is R. So we can see from bag B, we want one W and one R. So for each of these branches, we're going to have a W and we're also going to have an R. Now we can think of expanding our tree a little bit. All right. So after this first W pick, we also have a choice of R, because we do have an option after this. We still have the other marbles. All right. So after picking a W, we have a choice of picking an R. But on the very first pick as well, we have a choice of picking an R. All right. And after picking this R, we also have a choice that after this first R or the first red marble that we have picked, on the second pick, we'll get a W. All right. So it would be first we pick R and then we get a W, or it would be we first pick W and then we get an R. These are both different cases. We'll count them as 2 cases, for they're 2 different branches of this tree. So like this, we can see that each of these 4 branches are basically going to have further 2 branches. Let's write it down. We're first of all going to have, let's write down the base case. All right. We're going to have first of all 4 branches. All right. Because 3, 4, 5, 6, these will be 4 branches. The probability of getting the number again, that would be 1 by 6. And then for the chance of picking one white is 6 over 15. Let's deal with the white first of all. 6 over 15. All right, because we're choosing from bag B. So let's go for the white. It doesn't matter. You can also, of course, pick for the red as well, first of all, because they're multiplying in the end. So 6 white. So on the first pick, we're going to have 6 white, 6 over 15. And then we want to pick for the red. All right. So after that, after choosing 6 white, we'll have 7 red. Of course, for the red, we're going to have the same number because we haven't yet picked from red. But the total number would decrease because remember, we did not replace back the previous white marble which we chose. So we have taken out that one marble. Now this is one branch done, but we're going to multiply this all by 2 because you could pick the white marble first. This one is for the white marble and this one is for the red marble. You could pick white first and then the red, or you could pick the red first and then the white. So these are 2 separate branches and these can interchange. So that makes up for the 2 cases on each branch, and that completes our numerator. Next, let's go over the denominator. We want probability of the first being the one of the marbles being white and the other one being red. All right. So we have already dealt with one of the cases. Exact same we can copy down over here. 4 into 1 by 6 into 6 over 15 into 7 over 14 into 2, because of course it's also having the same probability in it. So we can count this as one of the cases, but we have another case. It's another alternate case. So we're going to add, of course, not multiply. Multiply would mean that we are not going across the same branch. We're going across separate branches again. So we're going to add. So y plus, we're going to add because we also need to count in the cases for when we are picking from bag A. So from bag A, suppose I would choose first of all red, but then after red I could choose white, or I could choose first white and then I could choose red. So the same idea basically applies. How many branches we have? We have branch 1 and branch 2. So we have 2 branches multiplied with 1 by 6 because that's the probability of picking any one number, 1 or 2, and then 6 over 15 for picking the white. All right, or you could pick for the red first of all, and then let's look at the probability of the red. We have probability of red 4. Oh wait, for the white it is 8 marbles, right? So this will be 8 marbles. This would be 8 over 15 for the white marbles. And then for the red marbles, it would be 4 over 14. 14 because we have removed one marble, of course. And then multiply this again by 2 because you could pick red first and then white, or you could pick white first and then red. And that completes the denominator. And then we can calculate all of this. That would be 0.724 as your final probability. Question number 4. The weights x kg of 120 students in a sports college are recorded. The results are summarized in the following table. Weight in kilograms, x less than 40, all of these data values, and then we have the corresponding cumulative frequency. Now we want to draw cumulative frequency graph to represent this information. Very easy. First of all, very important, you start with labeling the axis, because labeling the axis carries a mark. We would have weight, x, kg. Most of the time, just writing down whatever is given in the table above, right over here, will grant you the mark. So you don't need to come up with any name. Next, we need to think of some suitable axis. All right, what will be the scale on the y-axis and what will be the scale on the x-axis? On the x-axis, we have weight. So we can see we have 40, 60, 65, 70, and 100. And how many boxes we have? We have 1, 2. We'll count the main divisions. We can go for the smaller box as well, but I prefer to go with these bigger boxes. So we have this one would be 0. We have 1. We have 2, 3, 4, 5, 6, 7. So maybe we can start with a spacing of 20. That should be enough. We can try. So 0, then 20, 30, 40, 50, 60, 70, 80, 90, 100. So this is a good enough scale. It covers more than half of the graph, which is what we want. Okay. Now let's look at the cumulative frequency. For the cumulative frequency, we go up to 120. We can again start with the 20 scale. I think so the 20 scale would be good. 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, and that completes our scale. And again, this also covers more than half of the graph, which is exactly what we want. Now let's get to making the cumulative frequency graph. Now always we're going to make sure that we're going to mark with the upper bounds. Over here, we're already given the upper limits of each of these intervals. So it's a good thing. Sometimes they will give you an additional value 0x lesser than. So it's important you do not use that lower limit. You have to use the upper limit of each interval. So the first one is x lesser than or equal to 40. We already have that value. That will be over here. We can zoom in on this. The first value is going to be here. Let's have a much smaller pen. Nice. Okay, so the next one would be x lesser than or equal to 60. All right, and that would be at 14. So we have 60, right? And then we have 20 scale over here. And for each small box, we can just divide it. So the max value is 20, and we have 10 divisions, 20, 10. So each of these divisions is 2. So we have 2, 4, 6, 8, 10, 12, 14. 12, 14. So this will be our 14th mark. All right. Next, we want 38. 38 on 65. All right, so the middle value, of course, over here would be 70. So that means 65 lies in this center. And we want 38. So this is 20, middle value would be 30, and we have 32, 34, 36, 38. And this will be our value, 38. Right. Next value, we have 70, x lesser than 70. 70 is here, for which the value is 60. So this one is a nice value. We already have the scale for it. Be 60 over here. Then we have 85, and on the value 106. 85 again lies in this center, and 106. So 2, 4, 6. So this is 106. And then last value, x lesser than 100, and that would be at 120. So 100 is this, and 120 would be over here. And that gives us the plotted points. Now we can try joining them and make sure that it's a smooth curve, right? Now, of course, you don't want to just join it straight with a rectangle, straight with a ruler. So it's best if you make a smooth curve as much as possible, and as well as it should be accurate, because you're going to be reading off this graph in the very next question. They almost always ask you to read from the graph and give how many k students or how many values after this cumulative have this value and so on. like this, somewhat. It should be like this. So my drawing would be a bit inaccurate, but because of course I'm drawing digital, you can draw it much better while you'll be doing on paper. But yes, it can be more accurate than this. But just for the sake of showing, your graph should generally look like an S shape. So it should look like this S shape. All right, you can of course draw much better than this. This is just digital work. All right, so for part B, it is found that 35% of the students weigh more than WKG. All right, 35 students weigh more than WKG. Now, very important thing over here, cumulative frequency graph. The reason we call it cumulative frequency is that because it starts accumulating values. All right, so if you're going to suppose look at 20 over here, 20 cumulative frequency, you're going to get over here corresponding value for those number of students from the starting value. All right, so it cumulates from the bottom, like it starts counting from 0 at the bottom, then it builds up on the x values, the weights over here. So it cumulates. All right, so you want to basically start reading from the bottom, and over here they're saying it is found that 35% of the students weigh more than WKG. That is fine, but we want to know how much the students weigh less than WKG so that we can mark accordingly. So that we can easily find out. We just need to subtract it from 100%. 100% minus 35%, and we're going to multiply this with 120, that is the cumulative frequency, because we want it on the scale of the cumulative frequency, and that will give us 78. So 78 is the value which we're going to mark, and above 78 will be the 35% of the students which weigh more than WKG. And that's the way we read the cumulative frequency. Always if they say more than the value on the x-axis, we're going to first of all subtract it so that we can account from the bottom. So we're going to say 78 over here. We have 60, 70, 72, 74, 76, and then we have 78 right over here. Make sure you show it on your graph. It would be over here, somewhere down here, and that would be 70, 72, 74, and around basically 72, 74, 76. So your value of W would be 76. All right, this would of course differ if you have a different sort of graph. The mark scheme usually gives you a range of values for it, but the important thing is that you show it off your graph, because if you're going to prove it that yes, this is the value I got from the graph, you will get the mark. You just need to show it that it's on the graph. All right, so of course the value will vary. For me, I got 76. You can get a better value by drawing it actually on paper. So the value we got of W is 76 kg. Let me just recheck. 70, 72, 74, 76. Yes. Part C, calculate estimates for mean and standard deviation of the weights of the 120 students. Now, since this is a very lengthy, mostly data collection part, I've already done the working for this one. It's really straightforward. Of course, you first of all are going to find the midpoint, because it is part of the formula of finding the mean. You need to find the midpoints of all of the intervals. That would be 20, 50, 62.5, and so on. Then you multiply that with the frequency. All right. And the way you find the frequency is that we're going to go back to the table over here above, which I was changing, and you would see the way we're finding the frequency over here is that we're basically looking at the sum of the values. All right, the first one is 0. To what we add, to what value do we add to 0, so we get the next cumulative frequency, and that would be 14. So 14 is our next frequency value. Then what would we add to 14 plus 0, plus what will be that extra value that will give us 38? So we will just subtract 38 and 14, and that will give us 24. So 0 plus 14 plus 24 gives us 38. The same goes for 60. For that we get 22, because 22 plus 24 plus 14 plus 0 gives us 60, and so on. So we get the frequency values. All right, sum of all of these would be 8545, and from there you can find the mean, which will be the sum of all of the midpoints into the frequency values. over the mean over the frequency, and that would give us 71.2. For finding the standard deviation, we can look at the formulas, and we can see over here that we will have the sum of x squared into f. Over here, x we are having as the midpoints. So we're going to square the midpoints first of all, and you'll have these values. And then you'll add the sum of the m square into f values. So that would be these values. And then you're going to sum them, and then you're going to put that in the formula and get your corresponding standard deviation value. So most of this question is basically data collection. So if you are successful in finishing this data collection and calculating all of these values, so you're already done by the question. So this question is really easy, and you can easily score marks in this part. All you have to do is to be careful in finding these large numbers and so on. Question 5. The probability that a driver passes an advanced driving test is 0.3 on any given attempt. Deepak keeps taking the test until he passes. The random variable x denotes the number of attempts required for Deepak to pass the test. Find probability that x is greater than or equal to 2 and lesser than equal to 6. Alright, so first of all, they have said that the driving test probability of passing is 0.3 on any given attempt. On any given attempt basically means that if you're giving 2 tests, 3 tests, 4 tests, it does not matter. The probability of each test remains same, 0.3. Next, what do they say? He keeps taking the test until he passes. All right. So he keeps on giving the test until he passes. So suppose he fails, and then he passes. So he's going to stop right there. So this follows basically a geometric progression. All right. This essentially follow the geometric distribution, and one of the rules for applying the geometric distribution over here, all right, or the geometric probability distribution, is that we need to have a success condition. First of all, you need to know that will you have the probability of failure, and you'll have the probability of success. That's already defined over here. The probability of success is 0.3. Probability of failure would be 1 minus 0.3. Next, you need to know is that when will the probability stop? He will stop as soon as he passes, all right, or as soon as success event occurs. That is happening, so we can use the geometric distribution for this. All right. So random variable x denotes the number of attempts required, and again we're counting number of attempts. That's another requirement of the geometric probability distribution, that we're counting number of attempts until we get to the success. With all of those conditions satisfied, we can use that distribution. So x can be distributed as a geometric distribution, all right, and in that we're going to put a probability p. All right, and what do we want? We want probability of x being greater than or equal to 2 and lesser than or equal to 6. What does this mean? This means on expanding, we want probability of x equals to 2 plus probability x equals to 3, and so on until probability x equals to 6. Now, of course, there are other ways as well by using the other formulas, but I just use this method because it's straightforward. You can, of course, use the other formula as well for faster calculation. So once we expand this, we would basically calculate the probability of each of them separately, and you can even see in the formula list we are given how we can calculate for the geometric distribution. Probability would be the probability of success into 1 minus p, that's the probability of fail, raised to power r minus 1, which nth attempt we are doing. So we can write that down here. For probability of x equals to 2, that would be 0.2, and 1 minus 0.3 raised to power 2 minus 1 plus 0.3 again, 1 minus 0.3 raised to power 3 minus 1, and so on until you get 0.3, 1 minus 0.3 raised to power 6 minus 1. All right. Now, of course, make sure that you show all the probabilities because that carries marks. I'm just not showing them over here because it's, of course, understood you're going to add all of the probabilities. But do show them when you are writing them in the actual paper. And once you sum up all of these probabilities, you will get 0.582 as your final probability. Find the expected value of x. Expected value of x, 1 mark, then it should be really easy. You can go back in the formula, and over here, the only other formula which we've given is this, that the mean of geometric distribution is 1 over p. Now, many people forget that expected value of x also stands for the mean value of x, all right? So we already know that the expected value of x would be the mean value. That would be basically 1 over p. We got that formula from the formula sheet. It's the same as the mean value. 1 over p, probability of success, which is p is 0.3. 1 over 0.3, that gives us 3.33. Next part. 5 friends will each take their advanced driving test tomorrow. Find the probability that at least 3 of them will pass tomorrow. Now, the best way to attempt these questions is by making cases, because they said at least 3 of them. All right, there are many ways to attempt this. One of the ways is by doing binomial distribution. It's a nested binomial distribution. First of all, you'll find probability that the 3 friends will pass, then more than that, and then so on. But I can prefer to do it with case. Now, how do you do it with making cases? You first of all make some slots. All right, define the number of slots. Maximum are 5 friends, so there will be, of course, 5 slots. 1, 2, 3, 4, 5. All right, let's start with the base case. At least 3 of them will pass tomorrow. All right, so the number of pass, I'm going to write the pass as p and fail as f. Number of pass students should be at least greater than or equal to 3. All right, so we can fill in these slots p, p, p. All right, 3 people must pass, so of course the rest of them will fail. All right, then the next case, because they said at least 3 of them, so there will be still more. At least 3, so 3 or more. After this we have p, 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 and then p. 4 can pass, but 1 may fail. All right, then after that we have the last case, that all of them pass. So now we can find probabilities for each of these cases, alternate cases. So 3 of them will pass. Probability of passing is 0.3, but raised to power 3. Basically 0.3 multiplied 3 times into probability of fail. 1 minus 0.3, 0.7 raised to power 2, because 2 of them are failing. So 0.7 into 0.7. Now we're going to do another thing over here, and that would be 5 choose 3. Why are we doing this? Well, because there is no particular order to the people failing or passing. All right, I could have the person to first fail, and then the next person could fail, and then the third person could pass. All right, so in no particular order, any 3 of those people could pass. All right, so you need to account for all of the cases, and that's why we do 5 choose 3. You can also see how this is following a typical binomial distribution. Usually in binomial distribution as well, we do the same thing. We could really write this as a binomial distribution, that x, where x is the number of friends, is denoted by x, binomially distributed. Probability of the number of total people is 5, success is 0.3. And what this case was, basically this case was probability x is equals to 3, and that expands to 5 choose 3. That expands to 5 choose 3 into probability of success 0.3, and probability of fail 0.7. 0.3 raised to power 3 and 0.7 raised to power 5 minus 3, that would be 2. So you can see that the binomial distribution is also following this exact same pattern. That is why 5 choose 3 over here. So now it's your choice. You can either go by this method or this method, whatever way you find most comfortable. And that's why 5 choose 3. Next, similarly for the next case, we have 4 passing, so 0.3 raised to power 4 into 0.7. Only one person is failing. That would be 5 choose 4. All right, 5 choose 4. So we're choosing from these 5 people in no particular order, 4 people that will pass. Of course, you could also not do 5 choose 4 and just do 5 choose 1. That's the same number. You can pick up and select one of the 5 positions for the person who has failed. Even in fact, in the previous question, 5 choose 3, we could have done 5 choose 2, and it would mean the same thing. We could either work with the number of failed people and select them in those 5 slots, or we could work with the 3 people and select them in the 5 slots. So over here, we're working with the people who are in success. 5 choose 4 over here. Finally, the last case is 0.3 raised to power 5. And that's it. There are no people failed. In fact, you can even write 5 choose 5, but that would have no effect. 5 choose 5 anyways is 1. So it really does not matter. So the total, of course, or the total probability would be the sum of all of these. You add them, add all of these probabilities after you multiply them individually, and you will get 0.163. Next question. 75 people will take their advanced driving test next week. Use an approximation to find the probability that more than 20 of them will pass next week. All right. So the reason why I was specifying a lot on binomial distribution is because of this. Over here, we will be using a binomial distribution, and we are working with an approximation. All right. So what are we approximating in the first place? We will be starting with a binomial distribution like we did in the previous question. That whole pattern was based on a binomial distribution basically. So the same goes over here. All right. We can define x as the number of people who will pass, and then we can set up the statement binomially distributed as total number is 75 and the chances of passing are 0.3. Now typically they said probability of more than 20 will pass next week. That would basically be probability that x is greater than 20, and as you know, then you would have to sum for all of them all the way to 75. X is equals to 21, 22, 23. That is very, very lengthy, and so that is why we go and do the approximation. How do we approximate? We use the normal distribution. The normal distribution will basically simplify this working for us. Now to convert this binomial distribution into a normal distribution, we can rewrite it as normal, in which we need the mean and the standard deviation. How do we find the mean from this binomial? Really easy. The mean of this, we can go back into our formula sheet. Binomial distribution, the mean is NP. 75 into 0.3, that gives us 22.5. And then we need the standard deviation. We'll go back in the formula sheet. You can see that is NP 1 minus P, but be careful, that is standard deviation squared. So we will take the root. So that would be root 22.5 into 1 minus P, which is 0.7. That will give us root 15.75. So our statement becomes x is normally distributed as 22.5 and 15.75, and there you go. We have basically approximated into the normal distribution model, and now we can use the normal distribution table and its model to calculate the values. And now that we have approximated, we can now write the statement that would be probability of x is greater than 20. Now don't just go ahead and directly solve it. We have to apply one new thing, that is continuity correction. All right. Why continuity correction? It is something you do when you're converting from a binomial to a normal distribution. All right. You do it because we don't want to count this value of 20 in. All right. In the normal distribution curve, all right, in the normal distribution curve, generally for any single value, all right, even if I take probability of x is equals to x, probability of x equals to 20 on a normal distribution curve, the probability of that single value, of course, will be 0, because the probability of any value should be given in a range, right? It should be given in any some sort of range. An exact value will not have any area under the graph, and area under the graph is of course this probability over here. Since a single value has no area under the graph, it would be 0. So this continuity correction is basically what we apply to get an approximate answer that is close to the boundary, but of course not counting the boundary as well in the calculation, because we don't want to count the boundary in the calculation. So we are going to calculate a slightly bit ahead of it or include it based on the inequality we're working with here. All right. So that's a rule. Now, how do we apply this rule? Continuity correction. It is really easy once you understand it. And that is basically you want to exclude or include this boundary value based on this inequality. We want probability x is greater than 20. All right. So that means logically that we don't want 20 in this value. We don't want 20 in this inequality. So that means we're going to write probability of x is, that's why we wrote approximated sign, x is greater than 20.5. We always add or subtract 0.5. We added 0.5 because we don't want this boundary value 20. Of course, x is greater than 20, so all values above 20. So if we add 20.5 and that excludes that boundary value 20. And now we perform the standard things which we do. That would be standardizing it to a z value. That would be probability that z is greater than 20.5 minus 22.5 over root 15.75. All right. That would be probability that z is greater than minus 0.504. Now remember, the sign is greater than, we want to convert it to a lesser than sign, so we'll take the complement. That would be 1 minus probability is lesser than, probability c is lesser than minus 0.504. And now it's in this lesser than format, so we can bring in our phi notation. We can write in that notation form, so that would be minus 0.504. Make sure to also add minus 1. All right. Now since this is a minus value, we apply that same minus rule which we used earlier. 1 minus 0.504. That 1 and 1 basically cancel out, so we're basically left with 0.504. Now we can go and search in the table. Look at the z value, 0.5, we want 0, and then we want 4. So we add on to it 14. So that will be 0.6915 plus 0.0014. And that will give us the probability of 0.69, 0.6929. Three significant figures, that would be 0.693. That's your final answer. Question 6. Jai and his wife Kaz are having a party. Jai has invited 5 friends and each friend will bring his wife. At the beginning of the party, the 12 people will stand in a line for a photograph. How many different arrangements are there of the 12 people if Jai stands next to Kaz and each friend stands next to his own wife? Alright. So for Jai and Kaz, we can use the small letters J and K. And for wife, we can use W. For the husband, we can use H. Alright. Now, always for these questions, I prefer doing it using the slot method because I clearly then know where am I arranging the items. All right. We have 12 people, so we'll be using 12 slots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is really helpful and it really helps to mitigate any sort of blunders or silly errors. So we want Jai next to Kaz. We want them always together. So we're going to put this box over them. All right. And I'll tell you why in a minute. And then we want each of the wife next to their own husband. So husband and then wife, husband and then wife, husband and their wife, husband and their wife, and so on. Each of them together. All right. We want them to be always together. So they're sort of like this in a box. All right. Now, why we put them in a box? Generally, when we do arrangement, or let's suppose if this was unrestricted arrangement, we would just straight away do 12 factorial. All right, that would just arrange these 12 people in a line in total. But that's not what we want today. What we want is that we want these people to be arranged in such a way that these two are together and then each of these two pairs are together as well. And that is the reason why we drew the box. All right. So first of all, let's look at all the different ways we can arrange these sets of people in the line. All right. We have 1, 2, 3, 4, 5, 6 sets. All right. So they can be arranged in 6 factorial ways. All right. They can be shuffled in 6 factorial ways. Now we can look within each box. Within each box, we have 2 factorial. All right. So now don't just go ahead and write a single 2 factorial. No, a single 2 factorial is for just a single set. If I write 2 factorial once, that means I'm just arranging, suppose let's take j and k, I'm just arranging them so they can be k and j, or j and k can be arranged in those two ways. That's it. That's just for one box. But I need to account for the arrangements on each of these boxes. It may be in this box I can have W and H first of all, or maybe in this box I can have W and H first of all. Alright, so any of them can shuffle and switch their places, and we need to account for each of them because they are a unique arrangement. That would mean 2 factorial raised to power 6. Alright, now don't worry because it's a power, it's basically just meaning that we multiplied 2 factorial 6 times. 1, 2, 3, 4, 5, 6. 6 boxes. Multiply all of this together, so 46080. Also, we multiplied all of this because we want all of these cases to happen at the same time simultaneously. So that would be multiplying. 46080 is your final answer. Part 2. How many different arrangements are there of the 12 people if Jai and Kaz occupy the two middle positions in the line with Jai's 5 friends on the one side and the 5 wives of the friends on the other side? Again, we have 12 slots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright, we want Jai and Kaz to occupy the middle place. Alright, so that would be J over here, making sure 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So this should be J, okay, and this should be K over here. Actually, wait. So J over here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 is so K over here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we have them exactly in the middle. Again, we want them to occupy the two positions in the middle and just stay over there. They are fixed in the center. Alright, and then what did they say? They said that Jai's 5 friends will be on one side. We can say them all as male. So all of his friends on one side, and then all of 5 wives on the other side. So female, all of them on one side. Alright. Now they said all of the males on the one side or all of their females on the other side. So again, these are grouped. Alright. Now how will we come to arranging them? First of all, start with each of the boxes. For the fixed one, we can have J and K or we can have K and J. Alright. So in the center itself, we have 2 factorial. They can shuffle in that way. Alright. Now look at either of the boxes on either of the sides. These 5 males, they can be arranged in 5 factorial ways. I can have any of these males standing here in the first slot or in the second slot. They're all distinct items. So all of these people can be arranged within this set. Similarly, that applies for the females. They can be arranged within this set in different ways while still being in this same slot box. Okay, but we now have another thing to add, and that would be multiplying with 2. Why? Because all of the males can be here, but the males can also be over here. Alright, this whole set could be on the right side, and this whole female set could be on the left side. The question did not specify that they will be always on the left. They said they could be on either sides, but all the males and all the females must be together. So these two sets can also switch places, and for that we multiply by 2. So that would be 5, 7, 6, 0, 0 as the total number of arrangements. Part B, for a competition during the party, the 12 people are divided at random into a group of 5, a group of 4 and a group of 3. Find the probability that the Jazz and Kai are in same group as each other. Very important, we are working with division into groups. That will be working with NCR. Again, slot case making. Alright, so let us see, what do we have? We have a group of 5. So 1, 2, 3, 4, 5. Then we have a group of 4. 1, 2, 3, 4. We have a group of 3. 1, 2, 3. Alright. What can be one possible case? We want Jai and Kaz to be in the same group. Alright. So I can put them in the same group like this. Now the way we approach these questions is, right, we always first of all make the slots, make the available positions, and then we fix the items that we can fix. Over here, I'm fixing Jai and Kaz. That means I'm already pre-selecting them. I don't need to select them again or worry about selecting their positions. Alright, I've already made one case and I've set them in the group 5. Now they will remain there. I don't need to select them. But we do need to select the other people. Alright, so out of the remaining 12 people, we have selected 2 people. So 12 minus 2, we have now 10 people. So in 10 people, we can select 3. Alright, so that would be 10, choose 3 for this. Of course, you can just select from, just select for any of the groups. I could even select for the 4th group first. It does not matter. The order in which you select the groups does not matter. We just need to divide them. And that's what's important. So it doesn't matter if you select for this 4th group first or the 3rd group or this 1st group. You just need to select them. So 10 choose 3 for these 3 first slots into 7 choose 4. Now why 7 choose 4? Because after we selected 3 from the 10 people, we have now 10 minus 3, 7 people. And from the 7 people, we will select into 4. Of course, you can select 7 choose 3 as well. It does not matter. And remaining 7 minus 4, we will have 3. So that would be 3 choose 3, or they are basically automatically selected because there are 3 people left. They have no other place and they'll just take those 3 slots. That leaves you with 4, 2, 0, 0 selections. Now this is not done over here. We have another case. Again, we make the slots. Now we may have another case where Jai and Kai will be arranged in this slot. Alright. Another important thing to note is that I can place Jai and Kai over here, but something like Jai over here and Kai and Kaz over here on this place, Jai over here and K over here, does not change the order of division. Again, 10 choose 3, same number of people will be selected, and Jai and Kaz are still in the same group. This does not change the way of dividing the people. So do not think that this is a separate case than this case. They are still counted as the same case. But what is counted as a different case is if they're itself in a different group. Alright, and each of these groups are of course distinct because of their sizes. If they were not, then we would have to divide them by the repetition or just not count those groups. Alright, then we would have just ended on the first case. But over here we have different sizes of the groups. So now we're looking at the case where J and K are in the 4 number group. Now we have to do 10, choose 1, 2, 3, 4, 5. So 10 choose 5. So 10 minus 5, that would be 5. Then we're left with 5 choose 2. Choose these 2 people. And then remaining 3 choose 3 again. So 2, 5, 2, 0. Again, I'm saying you can choose for any group. It does not matter that you choose first for the 5 number group and then for this and then for this. You can go in any order. You'll still get the same answer. Then last case 1, 2, 3, 4, 5. 1, 2, 3, 4, and then 1, 2, 3. And now you can see where I'm going. That would be J and K in this set. Alright, so 1, 2, 3, 4. 1, 2, 3, 4, 5. This is a separate here. So we're going to again do 10 choose 5 into 5 choose 4 because we want to choose 5 people in this set. And then lastly 1 choose 1. It's really not important if you write these last ones, but maybe if you want to write it for clarification, you can write it. It's really no issue because they all simplify to 1. 1 choose 1, 3 choose 3, and so on. So this gives us over here 1, 2, 6, 0. Alright, and these are all alternate cases. Either one of them can happen, so we add them because or the first case or the second or the third case could happen. That means we're going to add them. So total cases over here, we can add them, and that would be 4, 2, 0, 0 plus 2, 5, 2, 0 plus 1, 2, 6, 0 is 7, 9, 8, 0. Now, most students forget the part that this is not just a selection question, it's a probability question. You have to calculate the probability as well. The probability which we are working for, that would be 7980 over the total cases. Now, what are the total cases over here? Total cases are basically the unrestricted cases over here. Suppose you have no restrictions, no nothing. So how would you calculate the total cases? Then if you have no restrictions at all, you will just simply select from the people. So 12, choose 5. Why 12 choose 5? Because we are now selecting it unrestricted. So suppose you just have empty slots and you're going to select from the 12 people. That would give you your total cases with no conditions. 12 choose 5. That would be then 12 minus 5, 7. So 7 choose 4 for the next group. 7 minus 4 then 3. So 3 choose 3. No need to write it again, but for the sake of clarification, you can always write it. That gives you your denominator. And that simplifies to 0.288. All right. So this was the end of our statistics paper. Hope you had understood. Please leave a like, subscribe, and if you don't understand any question, do comment down under the video, and I will see you in the next one. Goodbye.